So today we're going to cover two things: changing bases and the skill of changing bases, what it does and how we can use it to solve equations and also express equivalent functions. So let's talk a bit today about equivalent functions first. So equivalent functions are functions that look different, but when you graph them, they're the same. So for example, going back to a linear mx plus b, if I gave you y is equals to 3x plus 4, and if I gave you y is equals to 2x plus x plus 4, they look different, but when you actually graph them as is, without simplifying, you end up with the same graph, because, well, 2x plus x gives you 4. In other words, we're trying to create something that's identical, or identical expressions. I'm not going to call it trig identities, but things that are identical. So if we look at the first function here, since we're talking about exponential functions, how can we write this out in a different way, but yet when we graph it, it will be exactly the same? Meaning if you put in an x value, you get the same y value. So we're going to work backwards here by changing bases. So 9 can be expressed as 3 to the power of 2. And if we don't want to have brackets in our exponential function, we just use the power rule and we get 3 to the 2x. So what that means is 9 over x, so 9 to the power of x is the same thing as 3 to the 2x. In other words, this function and these two functions, they look different, but they're exactly the same when we graph them. And how are we going to prove this? Well, there's a couple of ways. You can use Desmos, or if you really wanted to, the fundamentals of graphing points is sub in a value for x and y. So if you sub in 1 into here, you get 9 to the power of 1. If you sub in 1 into here, you get 3 to the power of 2, which is the same as 9. So we end up getting the same value. Or if you want to try a bigger number, such as, I don't know, 3, if you sub in 9 to the power of 3, you end up getting 81 times 9, 729. If you do the exactly same thing for here, you type in 3, you sub in 3, what's 2 times 3? So 2 times 3 will give you 2 to the power of 6, and you put in your calculator, you also will get 729. So in other words, these two equations or functions are identical, they're equivalent. So the next one is the following. So if I had to ask you, what is the base graph for this? Well, one would say, well, the base graph is going to be 3 to the x. Well, what has happened? What kind of transformations has happened from here to here? Well, it seems like the base graph, I'll put here base graph, has been shifted, I'll put here shifted to the left by 1, which is fine. So how is it that we can express this in a different way? So what for the next two slides is going to be a bit more advanced. So if you feel like you don't feel comfortable watching this, you can just move on and fast forward to the next slide. So over here, I'm going to be using what we call the following. We're going to actually use an exponent law, which you've used many times before, but we're going to do it from a backwards point of view. So let's go back to the right hand side. I'm going to actually show this to you. If I say x to the power of 2 and x to the power of 3, what would you do? You would actually add the exponents, right? 2 plus 3 is 5. But if I were to give you x to the 5, what does that become? Well, it could become 2 plus 3, or it could become 4 plus 1. So we're breaking it up into pieces. So in other words, over here, I'm going to break this up into 2 pieces, but I know that when I break them up with the same bases, I add the exponents. So this works. I'm decomposing the exponents. And if I did that, I end up getting 3 to the x times 3. And I'm just going to put this 3 outside. So 3 over 3 to the x. So in other words, what's interesting about this is, I'll use a red pen here, is that, well, notice how the base graph is still 3 to the x, but now we have a value in front. So in other words, from here, from the base graph to here, I end up doing the following. I actually vertically stretch by a factor of 3. So in other words, this equation here is exactly the same thing as, they look different, but they actually come from each other, meaning we're using exponent law. So if I were to actually put this into Desmos and put this into Desmos, we would get exactly the same curve. So they are equivalent even though they look different. But the thing they have in common is that their base graph is 3 to the x. So in other words, a shifting left by 1 of 3x is exactly the same thing as a vertical shift by a factor of 3. And I'm going to show you this in the Desmos in the next slide. So here we have a Desmos where I drew the 3x already, so the base 3 of the x, so the graph swoops up, and I'm going to type in 3 to the power of x plus 1. So what should happen with this graph is this graph should shift a little bit to the left. So you can see the blue graph compared to the original red graph, it has moved a little bit to the left. Now, what happens if I do the equivalent expression, the one that we worked for when we used the exponent laws? It was 3 bracket 3 to the x, and what happens? Oh, if you notice, the green graph actually overlaps the blue graph. So what this means is that the blue graph and the green graph, I'll use the arrow here, so these two are exactly the same, they are equivalent. So what I'm trying to say is that from the red graph to the blue graph, it shifted a little bit to the left, or we can say that the red graph stretched by a vertical stretch by 3, they end up getting the same graph. So a shifting left by 1 of 3x is equivalent to vertical stretching by 3 of the base graph. So these are equivalent transformations. So here we have a similar question, but instead of shifting it to the left, we're shifting it to the right by 2. So in other words, the base graph is 3 to the x, but from here to here, we had to shift left to the right, right by 2. So we're going to use the same exponent laws. We're going to break this up using the multiplication. So keep in mind, when I multiply same bases, I just add the exponents. When I add them, I end up getting the original one. So I'm breaking it up, decomposing them. And when I do this, what happens to this number here? Oh, this is the same thing as negative reciprocals, because it's a negative exponent, 1 over 3 squared. And what is 1 over 3 squared equal to? 1 over 3 squared is 1 over 9. And I'm going to put that 1 over 9 in the front. So if you look at this here, what's happening to the base graph? Oh, it's being vertically compressed by a factor of 1 over 9. So I'm not going to do Desmos, it's pretty much the same thing. So what I'm trying to say here is this one here, which has been shifted to the right by 2, when we did some algebra, we end up getting a vertical compression of 1 over 9. So in other words, these two transformations, yes, they're different, but they are equivalent in terms of creating the same graph. So a shift to the right by 2 of 3x will give you the same graph as if the graph was vertically compressed by a factor of 1 over 9. So here we have 3 to the x, and in this second part of the video, we're going to solve exponential equations. So what does solving mean? Solving means when two things come together or two things intersect. In other words, here is a 3 to the x graph, this red one over here. I'll use a arrow, okay? And I want to know when the graph will cross y is equals to 9. So where's y is equals to 9? So I see 10. Oh, this is 9. So over here, this is the number 9. But where does the red graph actually cross the number 9? Oh, it crosses right over here. And what's the x value? Because we're looking for the x value. X value is 2. So that's what I mean by solving exponential equations, when they cross. So how do we do this from a algebraic without using Desmos? So what we're going to do the following is write down the function, and we're going to set it to equal to 9 because we want the function to cross 9. And we know based on this graph here, this is where the 9 is, and we know the answer is going to be somewhere around the 2 mark when x is 2 based on the graph. So how are we going to get 2 from the algebra as if we didn't have the graph? So how do we solve for this? Well, there's a couple of ways. You can guess 3 to the power of what will give you 9, or we can take it and break it down into several steps. In other words, we can actually use the skill called changing bases. Well, 9, how can we express 9 in terms of 3? Well, we know that 3 to the power of 2 will give me 9. And what's interesting about this, now look at the format. The bases are the same. If we want exactly everything to be the same, what that means is you want the exponents to be the same. In other words, x is equals to 2. So in the second example, we have a similar graph, a little bit different and shifted a little bit to the right. So here's our red graph, and we want to figure out where this graph will cross the 9. So over here, using the arrow here, what we have here is, here's 9, and we want to figure out where the graph actually intersects that the 9. Oh, and we go back down, and we know the answer is going to be 4. That's when the x is 4. So we're solving for the x value. So let's do this algebraically wise. So I'm going to move this over, and then let's actually solve. So we're going to copy down the original question and set it to equal to 9. And in this case, we're going to change the base to the same. Okay, so now the bases are the same. So the bases are the same, then you want the exponents to be the same in green. So I want the green parts to be exactly the same. So I just write out the exponent parts, and I want them to be the same. And what x value would make it the same? So this, you just bring the 2 over, add 2 to both sides, and you end up getting 4, just like that the picture the Desmos showed us. So here we have a different type of exponential function, and we want to figure out where the graph crosses the 10. So if you notice here, you see the 10. So at this time I drew a horizontal line, the blue line, and I drew the red curve here in Desmos, and you want to figure out where they cross. So right now we know that at 10 we go down, it crosses at 4. So how do we solve this algebraically? We do the exact same thing as before. We're going to write down the equation 3 x minus 2 plus 1 is equals to 10. Now, before we actually address the changing bases, we have one thing that we need to do. We're going to have to address this plus 1. So we're going to have to sort of isolate. So we want this by itself, the exponent, the base exponent by itself. So this plus 1, which is not part of the exponent form, has to be relocated or reformatted. So we're going to subtract 1 from both sides, and you end up getting 9. And over here, then we can change bases. So 9 becomes 3 squared. And now if you notice, our bases are the same. And so now we want the exponents to be the same. In other words, x minus 2 is equals to 2. You bring the 2 over, x equals to 4. So here we have another example where we have the red and the blue. So over here we have the red curve, 8 to the power of x over here. And then we have a horizontal line which is in blue. And we want to figure out where they cross. See this second gray dot here? And if I go down, I can't really exactly know exactly what the x value, but I know this number here is less than 1. So it's going to be a number between 0 and 1, probably a decimal place or a fraction that is less than 1. So let's have a look at the algebra. So on the right hand side, you have 8 to the x is equals to 4. Now, if you look at both numbers, it seems like they don't have anything directly in common, meaning we cannot change 4 to a base of 8 like the ones that we did before. However, 8 and 4 have something in common in terms of another base. Yes, they do have a base of 2. In other words, 8 can be written as 2 to the power of 3. I'll put x on the outside. And 4 can be written as 2 to the power of 2. So now we have the same bases. However, that left-hand side has brackets. I don't want brackets. So we're going to have to use the power law. So remember when power law says to multiply the exponent. So that's 3x equals 2 to the power of 2. So now we're in a position where the bases are the same. So I'm going to put a square on the bases. And if I want them to look exactly the same, to find the x, I want the exponents to be the same. So I'm going to put here 3x is equals to 2. And you solve for x. So you divide both sides by 3. 2 over 3, which is close to 0.666, and which sort of matches the location, the approximate location of the x value there. So in this case, we have to know how to change bases and be aware of our multiplication skills involving common factors. Okay, so this, we're almost near the end. 2 more examples. So this one here, I'm not going to involve graphs. Let's actually go directly into the algebra. So we'll have 8 to the x is equals to 0.25. All right, so if you notice, there's a decimal and then there's a whole number. They're not really directly connected to each other. However, when you have decimals, there's some decimals you can actually change directly into a fraction. In this case, 0.25 is the same thing as a quarter. And if you notice, oh, I see an 8, I see a 4, and I know from the previous example, they all have a common base of 2. So 8 can become 2 to the power of 3, I'll put x, 1, 4 can be written as 2 to the power of 2. However, if you look at the right-hand side, I'll put in yellow here, this whole thing is not exponent form. Remember, exponent form looks like this? That 1 on top has nothing to do, is not part of the exponent form. So what do we have to do? So this is where negative reciprocals will come back. In other words, here I'll just use the power law, multiply the 3x. In other words, remember the reciprocal means the negative exponents? This can be written as 2 to the power of negative 2 because it's the same thing as 1 over. In other words, now here we have a pure base exponent. So here's my base of 2. And here is my exponents. And I want the exponents to be identical because I want the left-hand side to look exactly like the right-hand side. And I'm almost there. I'm just going to make the green parts to be the same. And when I solve, I divide by 3. I get negative 2 over 3. So this is where the previous videos, when we talked about negative exponents, changing bases, those are key skills that will help you solve specific types of exponential equations. And the last example. So if you notice here, we have a pretty massive looking exponential functions. You got you got the A's, you got the P's, you got the Q's all involved. And you want to set it to equal to 51. You want to know when they cross. So how are you going to deal with this? So we're going to have to peel this. When I say peel, remove things one at a time. I'm going to put in yellow, this is my target. I want to have a base and an exponent at the very end. But unfortunately, I have two numbers that are in my way that are not part of the base exponent form. So what do we do first? Well, we're going to go backwards in BEDMAS. Instead of multiplying first, we're going to actually deal with the plus. So what's the opposite operation of plus? Minus 1. So I'm going to subtract 1 from both sides. That will give me 50. And then I can target the 2 in front. And what's the opposite of multiplication? We're going to divide. So we can divide everything by 2. So put here my steps, divided by 2, divided by 2. 2 divided by 2 is gone. Now you're left with the base and exponent. The right-hand side is 25. So the last step is, okay, well, how is 25 and 5 related to each other? Well, we know that 25 can be written as 5 to the power of 2. So now you're in a position where the bases are the same, and now we want the exponents to be the same. So in this case, I want x minus 1 to equal to 2. Bring the 1 over, that gives me 3.